So idempotent matrix possible eigenvalues will be 0 or 1 or both. Next, find involutory. Finished. Hereafter, orthogonal matrix we will see. By this equation, lambda equal to plus minus 1 coming, but orthogonal matrix, by this definition only we can't tell because we have contradiction. Orthogonal matrix by this equation, whatever we are getting, only telling 1 or minus 1 or both I can write, but this is not a true. Main problem coming because of this transpose. This is not a matrix polynomial or matrix equation. I will give one matrix that find eigenvalues and tell me your work. First day I gave now one matrix. First, this matrix verify orthogonal or not. Orthogonal, but you try. After that, find Eigen values. This two work you do. This don't write if writing anything. Okay, right, no problem. Right after that, this contradiction we will give. After that, I will write theory. Coming or not? Everybody came online student. Eigenvalues will be cos theta plus minus I sin theta. So eigenvalue is e power plus minus I theta. Theta is for all theta. 0 to 2 pi rotation. So two eigenvalues coming e power I theta and e power minus sin theta. So if theta value we will change, then our eigenvalues of this orthogonal matrix except plus minus 1, more we are getting x plus I y form. I also we will get, minus I also we will get, maybe 1 plus I we will get, 1 minus I we will get. Whatever theta value we will put here, x plus iy form eigenvalues we will get. We can't tell that orthogonal matrix eigenvalues are only plus minus 1. Okay. So this is the contradiction for this. So you write after that finally orthogonal matrix eigenvalues. Eigenvalues of orthogonal matrix are any scalar, right? We can't tell purely real, purely imaginary, scalar. And like that, more example have. That day also I gave matrix on 3 cross 3, 1, 0, 0 related this. All are orthogonal matrix. Every places eigenvalues like that will come. You can't tell. Sometime asking on example, orthogonal matrix eigenvalues are real, purely real, rational, imaginary, and all like that will tell. No commitment, scalar, false statement. If plus minus 1 giving only. Next, we will see for unitary matrix. Unitary matrix eigenvalues are coming unit modulus. Means whatever eigenvalue will come in that modulus, if you will put, one have to come. So we can tell lambda is equal to e power plus minus I theta form direct. So e power plus minus I theta form we can write. And by the help of unitary matrix, we can tell for orthogonal also again. But real unitary matrix means real orthogonal. Because unitary matrix eigenvalues are unit modulus. So real unitary matrix also unit modulus will happen. That is called a real orthogonal matrix. Orthogonal matrix we are telling is scalar. We can't commitment here. But if real I will add, then real orthogonal we can go only this type because unit modulus. Real case you can tell all eigenvalues like this, but only orthogonal matrix we can't tell like this only any scalar, but real orthogonal we can tell this type, no problem. Maybe complex orthogonal eigenvalues are any scalar, maybe purely imaginary, x plus I y form, but not unit modulus, no guarantee have. But real case, unit modulus must guarantee have by the help of unitary matrix. Last nilpotent matrix, check it. Nilpotent zero only will come all. Here apply everybody partition of matrix method. For eigenvalues also you can apply like this. P0, 0, Q. You find eigenvalues of P and eigenvalues of Q separate. That is the eigenvalues of A. Both are. And determinant also, determinant of P into determinant of Q. If trace asking, then trace of is trace of P plus trace of Q. So partition of method, matrix method, you can apply every places. Why this much time taking? What eigenvalue coming? Wait. Here tell. 1, 4, 2 plus minus I. Like this. Everybody coming this? Total 5 cross 5 matrix. No, 5 eigenvalue. 4, 2. For this 3 eigenvalue will come for Q. Comma 2. Means 4, 2, 2, 1 plus I, 1 minus I. What about other? For Q, means this eigenvalue is 4.
Determinant A32.
What Gita?
Determinant A32.
In this where mistake hai? 4 to 2, this complete changing or 4 and 2? Okay. For Q, remaining 2. What is this? Won't come.
4,
But
2,
1
plus
and
I minus I.
1, 1.
Yes.
2, 4, 4. 1, 1. You check it. For eigenvalue finding this much time don't take. Everybody check it. For 2 cross 2, 3 cross 3, this much time will take.
For determinant 32 answer.
But Gita?
Determinant 32 is answer, sir.
Okay, here after product you do all. Separate kind find. This separate find. This is separate find. Big equation will come.
Sir, eigenvector, should I want to check that eigenvector also?
Yeah, 12 how will come? 6 will come now. 2 AB, 2 3 is 6 now. Wrong calculating don't do. Correct. Equation find, one root find, after that division formula apply. Where for you problem? 3 cross 3 Q. Then wrong have. Product of eigenvalue determinant must will be equal. It equation and all correct have or not? Or you came? Shubhash coming or not? This 3 cross 3 have no whole cube square coming for you. Hmm? How? Is this lambda common have every places? Where common have? Lambda is multiple with this, not with everybody. How lambda will go that side? Hmm? Lambda is with every places, then only lambda is 0. No, that's lambda is here common have. Here common not have. No. Where? What is this? Here. This how you can put 0. Full common one. No. Lambda into whole common, then lambda will go that side. No. If this into this equal to 0, then lambda you can take lambda value 0. Here sum is there have. You can't take like that common. 3 cross 3 matrix have degree will be the 3 degree polynomial. 2 degree how coming for you? This right. Everybody leave it that. Practice do later. Every calculating is not good. Write this, not coming, then tell me later. And more question I will give. After finishing, I will give more question. Practice for eigenvalues, eigenvectors and all. Calculating correctly keep. Now whatever eigenvalue here wrote, that is correct only. 1 1 4 4 and 2. Okay. That eigenvalue try, not coming, tell me. First rank question, system of linear question, eigenvalues question and all practice. Take from books and practice, because that and a lengthy process calculating time. If your calculating will be good, then very soon answer can find. Next, algebraic multiplicity and geometric multiplicity. Algebraic multiplicity, geometric multiplicity, both are for eigenvalue only. In your matrix, you have whatever eigenvalue you are finding. In that, we will see that every eigenvalue, respectively, we will see how many time repetition have. That repetition counting we have to do. That is the algebraic multiplicity for that eigenvalue. Suppose 1, 1, 2 have. So 1, 2 time have. Eigenvalue is 1, 1, 2. So 1, 2 time have. 2, 1 time have. So algebraic multiplicity of 1 is 2 and algebraic multiplicity of 2 is 1. Just a repetition. Geometric multiplicity of that eigenvalue. Geometric multiplicity means total number of linearly independent eigenvector of matrix corresponding that lambda. Here lambda, two type of lambda. For this lambda, how many linearly independent eigenvector coming? That is called the geometric multiplicity of matrix A corresponding lambda equal to 1. And for this eigenvalue, whatever eigenvector will come linearly independent, that is geometric multiplicity of lambda equal to 2. Okay. So total number of linearly independent eigenvector of matrix A corresponding lambda, meaning that is the linearly independent solution of this homogeneous system of linear equation. Yesterday we discussed this homogeneous system corresponding lambda, whatever solution coming, that is only eigenvector. And from that solution, whatever linearly independent solution have, that only linearly independent eigenvector. And linearly independent solution, yesterday I told you, in homogeneous system of linear equation, total number of linearly independent solution is total number of arbitrary variables n minus r. So total number of arbitrary variables where? In this system, corresponding lambda, whatever lambda will come, for that separate system will generate. In that arbitrary variables, and total number of arbitrary variables is total number of variables minus rank of this matrix corresponding lambda. And that only formula yesterday I gave R. There R is a rank of matrix A. Here rank is A minus lambda I rank. Okay. Yesterday some question I can find eigenvalues and all eigenvectors and all. So whatever you did there, that only theoretical here we will discuss. Okay, how many eigenvalues came, corresponding eigenvalues, how many eigenvector came, linearly independent eigenvector, that you can understand from here. Suppose 3 cross 3 matrix have eigenvalues, 3 only will come, because n cross n matrix is n degree polynomial. So at most eigenvalues, at most means not. Eigenvalues are total n. No at most, no at least, total, either repetition or distinct. So here 1 2 time repetition have 3 1 time. So we can go algebraic multiplicity of lambda is equal to 1 is 2, and algebraic multiplicity of lambda is equal to 3 is 1. Okay. We have to discuss about geometric multiplicity of lambda is equal to 1 and geometric multiplicity of lambda equal to 3. So case first, if lambda is equal to 1, if you will choose, and if you will solve a minus I into x is equal to 0, then how many linearly independent eigenvector will come? So when case first you will go, then only two possibility will happen. Either only one linearly independent eigenvector or two linearly independent eigenvector. More than two not possible. Correct? Why not possible? Because a minus I rank is 2 or less, 2 not, less than equal to 2. So if rank is 2, I told already linearly independent solution is equal to linearly independent eigenvector. So n minus r. So n is 3. So 3 minus rank is 2, then one linearly independent solution, or 3 minus, if rank is 1, then two linearly independent solution. Okay. 3 linearly independent solution if you want, then rank 0 want, no? Correct. If in your mind coming corresponding one, 3 linearly independent solution, why not certainly? One eigenvector, two eigenvector, or 3 linearly independent eigenvector. So 3 linearly independent eigenvector means 3 linearly independent solution. And total number of independent solution is n minus r. So n is 3, rank is 0. And rank of given matrix is 0. This meaning that is a scalar matrix will come. So a minus lambda is null matrix will happen. But null matrix will happen means what is eigenvalue? Lambda is 113, no? Scalar null matrix not possible. Correct? So 0 rank not possible. So eigenvalues possibility only either 1 or 2. Correct? Next, here come. Corresponding lambda is equal to 3. If eigenvector, if you will find, then must only one linearly independent eigenvector will come. More than one not possible. You can't take any contradiction here. So here must n minus r, 3 minus rank of, means here if we will solve a minus 3i into x is equal to 0, then total number of linearly independent solution, here rank will be, must will be 2. Sometimes they are asking also, if your 3 have 3 matrix unknown, they won't give matrix. They will tell lambda is equal to 3, what is the rank of a minus 3i? Exactly they will ask. So must exactly 2 will happen, because corresponding 3, only one linearly independent solution will come. More than here one not possible. Yeah, for 3 only means total 3 linearly independent eigenvector. At most, either 2 linearly independent eigenvector or 3 linearly independent eigenvector. Means corresponding 3, only one will come. Here 2 not possible. Suppose you will tell x and y corresponding this, not possible. If suppose 4 2 you are telling, two possibility have, suppose that in your mind running, then matrix is 3 cross 3, then at most linearly independent solution will be 3. More than 3 not possible. So 3 independent eigenvector not possible. More than 3. Suppose this one, this two, okay, then this two and this two will happen. 4 linearly independent solution will show. That's not possible. No, 3 1 1 right, or 1 3 1 right, or anything right. 3 1 1 you write, or 3 1 1 3 1 right. That is not a problem. Whatever 3 have, algebraic multiplicity 1 have, no, must only one linearly independent eigenvector will happen. More than one not possible. Yes, algebraic multiplicity. Here 2 twice time have, so either 1 or maximum 2. More than 2 also here not possible. Here more than 1 not possible, here more than 2 not possible. Yeah, distinct. Yeah, must 1 2 3. From here only 1, from here only 1, from here only 1.
Sir, because of the repetition, the vectors are likewise, sir.
Not understanding, again tell.
Because of the repetition, lambda is 1 1.
Yes. Algebraic multiplicity twice time have, no. So more than 2 linearly independent eigenvector not possible. At most 2.
Okay, sir.
Any type of n cross n matrix you are choosing, if you are finding solution, then at most n linearly independent solution will happen for every lambda. Miss total. For algebraic multiplicity 1 is a minus I if you will solve. So here at most 2 linearly independent solution. Either 1 or 2. Here if you will solve this, then at only one linearly independent solution. Okay. Because of n minus r only because of this. Because this is completely depend on this matrix. Okay. So for this reason, here you can write geometric multiplicity of lambda is equal to 1, possibility is 1 or 2, and here must be 1. Must 1. Here rank 1, why not possible? If rank 1 here possibility, then 2 linearly independent solution will come. And this 2 linearly independent solution will come, then this cases 4 linearly independent solution will happen. And 3 cross 3 matrix, 4 independent solution, how possible? One case will fail, no? This is the contradiction for this. Okay. And if you will go by practically, then you choose any matrix. If distinct type you are getting only 1, then a minus 3i you do. Must 1 rank will come. Must 2 rank will come. Okay. So because of this, you can see that our geometric multiplicity either equal coming or less than coming. And this is the relation of geometric multiplicity and algebraic multiplicity for all lambda. Gm less than equal to am. For this, Shai Kishan told very good. If distinct eigenvalues have, then for every eigenvalue, algebraic multiplicity is 1 only. So geometric multiplicity must 1 will happen. Solution must will exist. You can't tell that maybe no any solution. Not like that. No, homogeneous. Must solution will exist. Must eigenvector will exist. So every case is only 1, only 1, only 1. You can write like this also. Are distinct, then algebraic multiplicity equal to geometric multiplicity equal to n. 1 for all lambda respectively. You can write all n eigenvalues also for your confusion. Next, you can write at most n linearly independent eigenvector. Another this also right about this rank must be if algebraic multiplicity of any eigenvalue is 1, then rank of A minus AI must be n minus 1. A is n cross n matrix. Then rank will be must be n minus 1. Because for this, if algebraic multiplicity 1 have, then linearly independent eigenvector will be 1 only. And linearly independent solution means n minus r. So rank must be n minus 1 will happen. N minus r. Then only one linearly independent solution will come. This understanding no formula. Here how n minus r writing. This is must be 2, then only one linearly independent solution will come. So any algebraic multiplicity of any eigenvalue of A is 1 have, then geometric multiplicity must be 1. Wait, you're right. Then geometric multiplicity of lambda is equal to A is 1. And then, so this 1 we want. For that, what is the rank of A minus AI? This. So n minus r, rank will be n minus 1. Then geometric multiplicity 1 will come. So then rank of A minus AI must be n minus 1. Understanding, no? This n minus 1, Jennifer, this n minus 1 understanding how writing? Yesterday eigenvalues, eigenvector you did, no? From there also you can verify every eigenvalue algebraic multiplicity and geometric multiplicity, you can check it. And practice more number of questions, then only these theories and all will be strong. Finished, everybody? So annihilating polynomial, minimal polynomial is very important definition. Very important, and more number of questions coming, we have to use. We have to use more from matrix theory, from linear algebra, related transformation, linear transformation, more places they will use this annihilating and minimal polynomial. Annihilating polynomial means just any matrix satisfying any polynomial, that polynomial is called a annihilating polynomial. Means x place you kept a and solved null matrix coming. That is called a annihilating polynomial. Degree, anything. Any degree thing they can give. No restriction that less than n, greater than n. Greater than n also possible, less than n also possible. Okay. Minimal polynomial. For that we want monic polynomial. For that separate monic polynomial definition I gave. Monic polynomial means in your polynomial highest degree of x coefficient must be 1. That is called a monic. So minimal polynomial we want lowest degree monic polynomial. Means this polynomial also annihilating polynomial only. But this annihilating polynomial degree must be less than equal to n and must be monic. So lowest degree monic polynomial annihilates by any matrix A and cross n matrix A is called a minimal polynomial. Means your minimal polynomial will be lowest degree we have to try and monic. And after that have to verify matrix A satisfying or not. Here degree less than equal to n. At first we will see minimal polynomial how to find. Annihilating polynomial last we will see. So first we will see minimal polynomial how to find. After that we will see how to find, not how to recognize annihilating polynomial. We can't find annihilating polynomial. What? Nothing to find. Which polynomial getting satisfied by matrix A, that is called annihilating polynomial. So either they will give, or two type of annihilating polynomial must fix up for every matrix. Minimal polynomial and characteristic polynomial. Yesterday we saw characteristic polynomial also annihilating matrix A. Every square matrix satisfies their own matrix. C of A equal to 0 we saw, so we can tell that every characteristic polynomials are annihilating polynomial. So for every matrix, two annihilating polynomial must we can find. That is called a minimal polynomial and characteristic polynomial. But how to find minimal polynomial? First we will learn that. Annihilating polynomial, know anything, very easy. We can write that C of lambda is also an annihilating polynomial. M of lambda is also an annihilating polynomial. C of lambda we can find A minus lambda determinant equal to 0. M of lambda also we can find. I will tell how to find. So M of lambda, C of lambda we can find. Annihilating polynomial have no formula that okay, by this formula new any polynomial coming, that is annihilating, not like that. If we have matrix A is an n cross n matrix, then two types are annihilating polynomial. At least, maybe any polynomial I can satisfy. Myself I will prepare. But these two, 100% guarantee we can find anytime. Not only two. So first we will see how to find minimal polynomial. After that, what is annihilating polynomial? After that, three types of polynomial with us have: characteristic polynomial, minimal polynomial, annihilating polynomial. So we have to compare also hereafter that what is the difference between all polynomial, how to find, how to catch in exam hall, how to use, which polynomial will give, then which type of behavior we have to think. Okay, so C of lambda we know, M of lambda we will find. After that, H of lambda. This right first. So minimal polynomial, how to find? Minimal polynomial is very easy. Sometime very tough. But when more tough have, that time also we have to take some decision and then we can make easy method. So two type of method we will learn. First common method, another one, that method every places we can't use. We can't use first, we can't find by that method. So M of lambda we can find by C of lambda itself. Any matrix minimal polynomial asking, you find first characteristic polynomial. After that, possible minimal polynomial we can find. So minimal polynomial degrees are less than equal to n only. Suppose I have lambda minus 1 whole power 4. This is the characteristic polynomial any matrix I have. So possible minimal polynomial you have to find. And if we have matrix, then after that exactly minimal polynomial we can find. So first possible minimal polynomial, same characteristic polynomial, just power decrease. Partition method can apply and can decrease. Okay. So possibility for minimal polynomial. Hereafter, minimal polynomial definition telling lowest degree monic polynomial. So we have matrix A, anything matrix A we have 4 cross 4. That matrix characteristic polynomial is this. So possible minimal polynomial we can write. After that, whatever matrix we thus have, that matrix you put from lowest degree and check it satisfying or not. From lowest degree. From starting, don't check. Because C of lambda must will satisfy by Cayley-Hamilton theorem. Every square matrix satisfies their own characteristic polynomial. So this is same C of lambda only. Here you will put must satisfy will come. So this is the minimal, not like that. We have to check from lowest degree. So lowest degree is first one. If a minus identity means lambda plus a you put and solve. If 0 coming, then this is minimal polynomial. And if lowest degree satisfying, then every power will satisfy after that. When power 1 satisfying 0 coming, the power 3, power 4 must will satisfy. Must after solving 0 will come. So first lowest degree whatever will satisfy is our minimal polynomial. But suppose not satisfying, the next lowest degree you try. If this will satisfy, then this is minimal polynomial. Again, suppose if this is not satisfying, then next lowest degree you try. If this is satisfying, then this is minimal polynomial. Again, if this is not satisfying, then this must will satisfy, because this is characteristic polynomial, and in this case c of lambda and m of lambda both will be equal. If all lowest degree will fail, then c of lambda m of lambda will be equal. Understood? So this is a very easy method, but sometime no very big characteristic polynomial coming means that maybe you will feel tough, but this is only proper method. Suppose 2 degree I will choose, means 2 eigenvalues. Suppose I will choose lambda minus 1 whole cube, lambda minus 4 whole square. Then possible minimal polynomial what will happen? First same will happen, c of lambda itself. Next, three power will decrease one time, and this will decrease one time. Another one lambda minus 1, lambda minus 4. Correct? Means you can do one thing, 3 2 3 1. After that 2 2 2 3 sorry 2 2 2 1 2 1 did not doing. Another one 2 1 do otherwise. Possibility correctly write. Understanding how I am writing? Just one power have to decrease. 3 2 3 1. This is 3 2. 3 2 3 1. Hereafter from here decrease. 2 2 2 1 1 2 1 1. All possibility completed. Understood? Hereafter same type you start from lowest degree. Again, first you verify this a minus identity into a minus 4i, 0 coming on that. If coming, then this must minimal polynomial. Not coming, then next verify. And won't say how will satisfy, won't satisfy. Means you are telling separate minimal, means lambda minus 1 whole cube, lambda minus 1 4 whole, won't satisfy. How will satisfy that? Null matrix won't come. Every eigenvalues of characteristic polynomial must will contain in minimal polynomial. Maybe multiplicity will decrease or equal. Okay. So like that you have to verify. Next you have to verify this a minus I whole square into a minus 4i, 0 coming or not, have to check. If coming means this is minimal polynomial, not coming means next again you have to verify. Always you have to verify next. A minus identity a minus 4i whole square. If 0 coming means okay, minimal, not coming means again next. Again same type procedure always have to verify. Okay. You write this. This is just one roughly discussion. You write revision time, you will feel good. Anyone will satisfy. When another one thing, maybe here little bit confusion will come for you, because from lowest degree I told you, see, this is the 2 degree will come, this is the 3 degree, this is the 3 degree, both are 3 degree, this is the 4 degree. Okay, this is the 4 degree, no problem here. But here don't get confused, who will be the satisfying? Anyone will only be satisfied, both not possible to satisfy. If you, this is satisfying, that this won't satisfy. If this is not satisfying, same procedure only, you have to verify who is not satisfying, is next you have to verify. Okay, but when 3 degree polynomial have, then you have to go first who is satisfying. Must will satisfy, then must, that is the minimal poly. Both not possible to satisfy, because both are same degree. No, one have if degree increasing, then if lowest degree satisfying is, next degree must will satisfy. But when both are equal degree, then anyone will satisfy. Understanding what I am telling? This is 3 degree. Anyone will satisfy. Here I can't tell this satisfying means this must will satisfy. Not like that. Here power increasing. Here this satisfying means this must will satisfy. This must will satisfy. But here, if this satisfying means everything will satisfy. But if this is 3 degree polynomial, this is 3 degree polynomial, anyone will satisfy. Both not possible to set. Then how you will predict who is the minimal polynomial? Okay. Here, if anyone satisfying, then this must will satisfy, because here power again increased. Okay, so little careful. You write first, just a roughly discussion. You can add by your words also. Then next I will explain. Is everybody? So from here, two concepts we are learning, that whatever possible minimal polynomial have, finally, who will satisfy first, that will be the exactly minimal polynomial. So two, not three concept. First, that minimal polynomial is unique for matrix. More than one minimal polynomial not possible. Unique. Second, whatever minimal polynomial possibility have, every possibility is dividing the C of lambda. Means we can write m of lambda divide C of lambda. Dividing, no, from here only this decrease, this divide, this do, this divide, this do, this divide, this do, every places cancellation will go. So minimal polynomial is unique, m of lambda divides C of lambda, and every eigenvalues of C of lambda are eigenvalues of m of lambda, if and only if. Either every eigenvalues of m of lambda are eigenvalues of C of lambda. Only multiplicity decreasing only, no? You see here eigenvalues 1 and 4 have. Here every place is 1 and 4 have. Every possibility. Only multiplicity decreasing. Okay? So either multiplicity will decrease or will increase. So these three concepts must have to keep in mind. First, right? So this method, minimal polynomial method, this is very common method and general and good method. You can't forget. Means every time we can prepare. But sometime no, this must C of lambda also no need to find. By matrix entries itself we can find direct. Suppose I have identity met any order. These entries are diagonals are scalar like that. So whatever matrix define have, by that define itself, maybe little we will think means we can find direct. Whatever matrix entries given, by that entries we can satisfy one equation that is called a minimal polynomial. Finish. I can write a minus identity is 0. So minimal polynomial is lambda minus 1. Understanding? So this is very easy. Suppose I will use like that matrix also they will give. Randomly any matrix choosing we can't satisfy. So your matrix also full can tell a setting, full that shape, pharma. Means you can see, means you will see whole square, whole cube I will do and finish whatever coming. First power, whatever equation satisfying, that is the minimal polynomial. Suppose I will choose every entries are 1, 1, 1. This matrix, whole square if you will do, row into column, every place is 3, 3, 3 will come. Hmm? 3 I will take common, then every place is 1, 1, 1 will happen. Means same matrix A. So I can write that one equation I am getting that satisfying by matrix A. So minimal polynomial is lambda square minus 3 lambda. Finish. So whatever entries given have, by that help, if we can satisfy any equation, that is a minimal polynomial. Finish. You try another anything. One lowest means 3 cross 3 polynomial. So 2 degree is the lowest. 1 degree, what will happen hereafter? Hereafter greater this possibility. And no need to think this question why coming in mind, won't come. Because this equation I am not doing, this entry is doing. So this entry is what equation is giving you, that is our first degree can tell means satisfying. So that is the first our minimal polynomial, lowest degree minimal polynomial. This entry is giving, I am not giving. If your entry is not giving an equation, then you go by characteristic polynomial method. Understand it? So sum, this is also every place is not possible. Any randomly matter 1, 3, 5, 6, 7, 8, I can't do. Then we have to go by characteristic polynomial method. But sometime this is possibility. Means entries they will, this and all can tell one trick type. Looking itself, you can think this is that whole square. You see nilpotent matrix. Suppose I will write one matrix, nilpotent strictly triangular matrix 5, 6, 0. I told no, all strictly triangular matrix are strictly triangular nilpotent matrix. I told also if super diagonal or sub diagonal is non-zero, this is a 3 cross 3. So a power cube only 0 will happen. So here minimal polynomial for this nilpotent matrix is lambda cube. Means here C of lambda M of lambda will be equal. That matrix I gave no nilpotent matrix. I told 1, 1, 1, 2, 2, 2, and addition is subtraction. You told everybody told power is square only 0 will come. Told no. So minimal polynomial is lambda square. Finish. So by the help of entries, which equation satisfying first degree, maybe 4 degree also hereafter will satisfy. Not like that. After our solving, what first equation we are getting any degree equal to 0 coming, we can tell that that equation is our polynomial hereafter. Understood? So this is very rare you will see like this. You have to catch this matrix, that power must be 0 will come, or maybe to a I will add and I will see then 0 will come. Then you tell that is minimal polynomial. Must. Otherwise, we have to go by C of lambda. Suppose you can't find, then you find for the C of lambda. Sometimes this type matrix and all C of lambda also M of lambda will give. C of lambda little bit tough will go. 1 minus lambda whole cube. You will calculate more. No need. Sometime M of lambda will give you C of lambda. This matrix characteristic polynomial I can find by the help of this C of lambda, M of lambda, by this minimal polynomial. You think little. This minimal polynomial, what will give eigenvalues? 0, 3. Correct? By the help of, we know C of lambda, H of lambda, M of lambda. In this we know this and this, now we are learning how to find. But every polynomial equal to 0, lambda value whatever will come, that is eigenvalue only. But every eigenvalue have some, how to use that only I told, last I will discuss. What from here eigenvalue getting, from here getting, from here getting, what we will compare, what is the values of eigenvalue in our matrix. So just I am telling you, this is the matrix minimal polynomial I did. From minimal polynomial eigenvalues I am getting 0, 3. And by the help of here, I can write C of lambda. This is the 3 cross 3 matrix now. And this eigenvalues I am getting by the help of minimal polynomial. So possible eigenvalues of matrix A I can write. 3 eigenvalue minimum and no. And just now I told you that every eigenvalues of C of lambda or every eigenvalues of M of lambda are eigenvalues of C of lambda. All repetition maybe will increase. So here eigenvalues of M of lambda we know. So for C of lambda repetition will increase. So what repetition will come? 0, 0, 3, 0, 3, 3. Only 2 possibility. Because 3 cross 3 matrix. 3 eigenvalue we want. But 2 eigenvalue here have. I can't write 0, 0, 0. I can't write. Because every eigenvalues of minimal polynomial are eigenvalues of C of lambda. This is I am writing possible C of lambda. Exactly later I will tell. So this eigenvalue I can't write. 3, 3, 3, I can't write. Because here 3 missing have, here 0 missing have. So this 2 possibility not possible. Understanding? So 0, 3, here 0, 0, 3 I wrote, here 0, 3, 3 I wrote. But hereafter exactly how to find? You come in matrix. What is the trace of matrix? 3. Trace of matrix is
3.
3. And we have 2 possibility for C of lambda. Which possibility trace 3 giving?
0,
First,
0,
second.
6.
So second is not possible. Because sum of eigenvalues are trace of matrix. 2 possibility have. In that one possibility 100% wrong. Because trace 6 coming. But we want trace 3. So finish. So this meaning this is the exactly characteristic polynomial. And your characteristic polynomial will be lambda square, lambda minus 3. Minimal polynomial what have? Here lambda common will come. Lambda into lambda minus 3. Understand? So sometime by the help of minimal polynomial we can find C of lambda. Okay? Right. This everything right. This all are example one by one. By your language you write. Hereafter we will discuss annihilating polynomial. Question I will give last. Theory will finish after that. That time you find minimal polynomial and all. When all eigenvalues are distinct, that time C of lambda, M of lambda same. Okay. Then only one possibility will be there. C of lambda, M of lambda, both are equal. Here exactly eigenvalue we can tell 1, 1, 1 now. Yeah, all eigenvalues are 1 only. 3 eigenvalues. C of lambda, here lambda minus 1 whole cube, no. But M of lambda is 1. Lambda minus 1. So here lambda is equal to 1 only one time have. Minimal polynomial giving only one type of eigenvalue, that is 1. So must be all eigenvalue 1, 1, 1. If other any possibility means, then we can think okay 1, 1, 2, 1, 2, 2 like that. But only one possibility. So all eigenvalues 1, 1, 1. We'll see. We will discuss here after possible eigenvalues only, but h of lambda little we will discuss after that. So if we have n cross n matrix, then we can find C of lambda by A minus lambda A determinant equal to 0. When C of lambda we can find, after that M of lambda we can find by the help of C of lambda. Okay. So every n cross n matrix, if they will give any n cross n matrix, then two type of polynomial must we can find. Exactly we can find. And both are annihilating polynomial. Annihilating polynomial have nothing formula that this formula apply, one polynomial I got, that is annihilating, nothing like that. If exactly matrix given have and asking what is the annihilating polynomial of this matrix, then both you find and tell both are annihilating polynomial. Or if maybe any option they are giving C and D, so just you verify. If your C option h of a0 giving, then C option also annihilating polynomial. If your D option h of a0 giving, then this also annihilating polynomial. A polynomial satisfies by matrix A, that is called annihilating. Finish. No other formula. C of lambda have formula, no? Or M of lambda can find by the help of C of lambda. But H of lambda, nothing like that. Which matrix will satisfy by any polynomial, that is called that polynomial is called annihilating polynomial. So two must will be there. Another we have to verify. Okay. But they are not asking annihilating polynomial find. You have to catch this is annihilating polynomial. Always you will see in exam hall they are giving question n cross n matrix satisfies an equation. We are seeing in idempotent matrix also. Suppose I will write like this. Or anything, any equation, I choose idempotent, anything. If they are writing this satisfies or annihilates, like that writing, this meaning this equation will give one equation. I can write this polynomial is called annihilating polynomial. So our annihilating polynomial is lambda square minus lambda. Okay. I can't tell this is C of lambda or M of lambda. We can't tell. Satisfies one equation giving, that is only name is annihilating polynomial. And C of lambda, M of lambda we can find when we have given exactly matrix. Otherwise we can't find. Or C of lambda given have, then possible M of lambda we can find. Exactly we can't find. Possible. If C of lambda, M of lambda exactly want, what is the exactly minimal polynomial? Then exactly matrix one. Okay. But here we can't tell. Don't tell this is C of lambda, maybe M of lambda. No, nothing. Only H of lambda. Okay. So this annihilating polynomial, then equation form we will write. Then this also will give values of lambda. That is called eigenvalues. C of lambda, M of lambda, H of lambda. Everybody will give lambda value. All are eigenvalue. But which eigenvalue, what use, we will see later. First here you see this is annihilating polynomial, and by this annihilating polynomial possible eigenvalue you can write. 0, 1. So we can write also possible. Already I told by another method, possible eigenvalue of idempotent matrix either 0 or 1 or both. So by this annihilating polynomial method also we can find possible eigenvalue. Okay. But if we are writing characteristic polynomial from annihilating polynomial, then how to write? From here we are getting 0 and 1 eigenvalues of matrix A by annihilating polynomial. So possible C of lambda we have to find. Suppose A is our 3 cross 3 matrix. Then how type possible we can write possibilities if you are getting eigenvalues from annihilating polynomial? I told eigenvalues if we are getting from minimal polynomial, then every eigenvalues we have to write for C of lambda. All eigenvalues are eigenvalues of C of lambda. All. But for annihilating polynomial, not like that. I can write this possibility also. This also. 4 possibility I can write. Understood? 4 types of possibility I can write. So our characteristic polynomial, here this, here this. Anything, either 4 cross 4 also, any order. First possibility is this. Five possibility. But if this polynomial, if they will write, they are writing like this, so this possibility. And by possibility also they are asking, sometimes they will ask possible trace, possible determinant. So possible trace and determinant also we can write. Okay, they will give matrices satisfying this, then possible trace option they will give. So you can do possibilities and you can write trace and determinant. I have no place, I want place, you write this. Then next I will discuss. Only one possibility. Exactly without matrix, how can tell? Exactly trace, exactly determine matrix one. Here, infinite number of matrix will satisfy this. Idempotent matrix, not only one or two. Infinite, uncountably infinite. Finished, everybody? Suppose they now satisfies telling further this is annihilating polynomial. If that cell will tell matrix A has minimal polynomial satisfying this m of lambda, means matrix A satisfies minimal polynomial. They itself will tell minimal. Then you can consider, okay, this matrix what equation satisfying? This is not minimal, this is. And hereafter, whatever eigenvalues we are getting, that is from minimal polynomial. And from minimal polynomial when we are getting, then 0 or 1 don't write, both want must. Because whatever eigenvalues you will get from minimal polynomial, both are eigenvalues must for every possibilities. Maybe multiplicity will increase. So this possibility not possible, this possibility not possible, this is possibility. Understood? All eigenvalues of minimal polynomials are eigenvalues of characteristic polynomial, all. Same here also, this not possible, this not possible, only this three possible. So by the help of minimal polynomial possible determinant trace, these two only, these three only, possible minimal polynomial trace and determinant. Understood? So this is the difference between annihilating and minimal. Right again. another one thing you have to care. Suppose, finish writing, finish first. Another one thing we have to care. Suppose they will give minimal polynomial. A has minimal polynomial, direct polynomial form also they can give, lambda q minus lambda. Or A satisfies minimal polynomial. Satisfies minimal polynomial A cube minus A. Just one power I increased. Then what will happen? And this is a minimal. And again we are getting eigenvalues from minimal 0, 0, 1. And here order also n cross n greater than equal to 3 want minimum. So eigenvalues 3 coming. So greater than equal to 3 must be 1. 2 not possible. 2 cross 2 matrix you can't take here example because already 3 eigenvalues getting from minimal polynomial.
Sir,
And
lambda.
all eigenvalues of matrix A are eigenvalues of characteristic polynomial. So 3 eigenvalues we are getting from minimal polynomial. So must order is 3. If this is annihilating polynomial, then 2 cross 2 no problem. Okay. So why I increased little? Because again I am repetition doing all eigenvalues of matrix A getting from minimal polynomial are eigenvalues of C of lambda. Here after repetition also you have to care. All eigenvalues means every repetition must 0 2 time have no. Every repetition must 0 2 time want. Because M of lambda divides C of lambda. So, possible eigenvalue of, otherwise hereafter write all eigenvalues of matrix A 0, 0, 1 getting from minimal polynomial. This is very important. Getting from where? Minimal or annihilating? So 3 cross 3 minimum order. And if 3 cross 3 means how many possibility? Only one possibility. 0, 0, 1. I can't write 0, 1, 1. I can't write. I can't write 0, 0, 0. I can't write 1, 1, 1. Understanding? So by only one possibility, trace will be 1, determinant 0. 4 cross 4. Only two possibility. You can't write only 1, 0. You can't write this possibility. 0, 2 time must want. Okay. So only two possibility. By this trace is 1, 0, 2, 0. Understood? Clear minimal polynomial and annihilating polynomial. Hereafter another equation I will do. Complex. If eigenvalues are complex form, then what we will do? You write first this. Then which type of possibilities possible? You can increase possibilities. Suppose 5 cross 5 by your choice practice you can increase. Three possibility. n greater than equal to 3. Suppose 2 cross 2 matrix, then possibility tell. Yeah, you have eigenvalue no 0 0 1, not possible, so 2 cross 2 not possible. If annihilating, they will write, they will tell matrix A is annihilating, only satisfying. Annihilating means no problem, any order. Then 0 0 also I can write, 1 1 also I can write, 0 1 also I can write. Annihilating, no restriction. Because minimal polynomial, how many eigenvalue have? Every eigenvalue, every possibility want, but not for minimum annihilating. Then 1 2 time will happen now. We can change equation, correct. One, then what we will do, lambda is square. Okay, equation change, no problem. Now correct. Everybody finished? Like that, more words they are using. A satisfies and relates such that defined one equation type they will give. So how type behavior we have to do? So anything like that, any equation giving, direct annihilating. When we have matrix say exactly, then only exactly C of lambda we can find, exactly minimal polynomial we can find, otherwise no. If they will tell this is a minimal polynomial, then minimal polynomial type behavior you keep, otherwise only annihilating polynomial. Okay, so we'll see here what type of we have to do. So A satisfying this, so from here we will get one equation. So this is called annihilating polynomial. So by annihilating polynomial eigenvalues we will find. So this is cube root of unity will come. Just 1 omega omega square. Omega value e power 2 pi I by 3. Correct? So whatever eigenvalues we are getting, all eigenvalues of matrix A are getting from, especially I'm writing this is only because of you. Don't forget from where getting an eigenvalues, that keep in mind. Annihilating polynomial or minimal polynomial or characteristic polynomial. Every place is different behaviors have. So here whatever eigenvalues we are getting from annihilating polynomial 1 omega omega square. Next concept. Our eigenvalues are in complex, in conjugate pair. Okay. I wrote here only just n cross n matrix. So whenever eigenvalues you are getting in complex form, so just you go back and see our matrix A, they are given with real entries telling or complex entries telling. So two type of behavior possible characteristic polynomial will define. If real entries means how type possibility, if complex entries means how type behavior, possible characteristic polynomial. So if real entries have, if matrices is real matrix, because these are possible eigenvalue of matrix A and complex eigenvalue. So when our matrix has real entries, then our characteristic polynomial coefficient will be real coefficient, and real coefficient polynomial, if any value giving, then that value real giving means no problem, complex giving means must be want in conjugate pair. Complex solution of real coefficient equation must be a conjugate pair. So our possibilities we have to write in the form of conjugate pair. Otherwise, no, we can't write. Complex means no problem. Complex entries, polynomial, anything you can write. No conjugate pair, no guarantee. Conjugate pair also, otherwise no also. Purely real, purely imaginary, conjugate pair, non-conjugate pair, anything you can write. Okay. So first case we will go. A has real entries. Then we have to write possible C of lambda. Suppose first 3 cross 3 I will write. And eigenvalues getting from annihilating polynomial. So first possibility 1 1 1, and second possibility no other possibility. We can't write one possibility. I wrote. We can't write. Why? Because here conjugate pair not have. Omega writing means omega conjugate pair, omega square must want. Here omega square have, omega not have. Here for this omega square have. But for this every eigenvalue complex writing in real entries case, then conjugate pair must have to see in every possibility. So this 3 possibility not possible. Only 2 possibility for 3 cross. Determinant is 1. Trace and determinant. Trace is 3, determinant 1. Trace is 0, sum of roots, and determinant is whole cube, no, 1. Suppose 4 cross 4 matrix. 1 1 1 1, no problem. 1 4 cross 4 we can do. Omega square. Again omega square we can do. 1 1 omega square we can do. Enough. Hereafter can't do. Conjugate pair. Understood? Same trace and determinant, right? Trace will be here 4. Here omega cube plus omega cube. 1 plus 1 2. Omega cube 1 plus 1 plus 1 3. Here determinant is 4 1 1 1. Correct. Just product. Omega cube will be 1. Plus means here, no? What I did, minus 1 will come. Because 2. Omega plus omega square twice time. And minus 2 will come. Because 1 plus omega square is 0, minus 2 will come. Here correct have omega plus omega square minus 1 will come here. Because minus 1 plus 1 cancel, 1 will come. Now correct. Actually I multipled it. Omega cube. Right. Next complex entries I will write. Yes, everybody. Suppose complex entries. Complex entries means no problem. No need to take any restriction. Same type. Anything missing? Correct, no? Total 10 possibility coming. Then finish here after what? Trace and determinant, right? All are characteristic polynomial. Polynomial I'm not writing, no? Right, lambda minus 1 whole cube and all like that. So trace and determinant. Three omega square 2 plus omega. Write this and that here after what? So complex entries means no restrictions. All possibilities you can write. Conjugate pair also possible, non-conjugate pair also possible. So maybe hereafter, no any problem. C of lambda, M of lambda, H of lambda. Every polynomials are giving eigenvalues and every eigenvalues have their self values. Every places different concepts are there. Understood? No confusion? Hereafter, we will discuss nilpotent matrix possible minimal polynomial. And I told in definition that a power r equal to 0 and r is a least positive integer. Means nilpotency index that r will be greater than n, less than n. So that clearance we will do. So that index is completely depend on minimal polynomial. Minimal polynomial we are finding from characteristic polynomial. So if n cross n nilpotent matrix have, then characteristic polynomial must be lambda power n, because we know all eigenvalues of nilpotent matrix are 0. So possible minimal polynomial, what will happen? First same, just power will decrease, no anything. Lambda. Lambda is the minimal polynomial. In this case, just null matrix. Correct. Null matrix minimal polynomial is just lambda only. Means if A is your non-zero nilpotent matrix, then accept lambda. Okay. Means this possibility, then don't write. If your null matrix have that in index is only 1 only. So we can see that every cases index must be between 1 to n only will happen. Because A is a nilpotent matrix, then characteristic polynomial is this. Then our matrix possible minimal polynomial between 1 to n coming, this meaning every nilpotent matrix between 1 to n, any power must 0 will happen. If 3 cross 3 nilpotent matrix will choose, must that may be a square 0 or a cube 0. Power 4, no need to think. If power n 0 have, then must be greater than n power must be 0 will happen. But nilpotency index, what is this? That is greater than n possible. If A is a 4 cross 4 matrix, nilpotent matrix, then this is guarantee have C of lambda will be lambda power 4. So A power 4 must be 0 by Kelly-Hamilton theorem. And after that, R is greater than 4 means must be 0. Correct. A power 8, A power 10, A power 9, everything 0. But this R greater than 4 ham is, this is index, we can't tell. Index, this is not an index. But who is the index? So whatever matrix given have, so minimal polynomial we will find. Possible minimal polynomial, what will happen? Between 1 to 4 degree, maybe this, maybe this, maybe this, maybe this. If anyone is minimal polynomial, then index must be between this only, no? Greater than 4 must will satisfy. Either between anything satisfying means. But index possibility between 1 to 4 only. Understood? So we will write here nilpotent minimal polynomial is this only. So nilpotency index is equal to R, where R is this of matrix A. If non-zero writing means this one won't come. We'll start from 2. Understanding? If A is a non-zero, then nilpotency index is R, then 1 less than R less than equal to 1. And Understood? So any day in future, suppose they will give 4 cross 4 matrix. A is a 4 cross 4 matrix, satisfies a power 100 is equal to 0. Then what is the index? They will give different option. 100, less than 100, less than 4, greater than 4, between less than anything option. Maybe they will give first option 100, second option less than 100, third option 4 plus 4 have less than 4, and 1 less than equal to 4, less than equal to 4, like this. Less multiple choice means C and D both take out. Single choice, then only D take out. Understood? So power whatever 0 coming, that power is not an index. Don't tell that is the index. Index between 1 to 4 only possibility. What is order? Between 1 to n. Okay? Right. Hereafter we'll see after lunch, but little work I will give. Yeah, this index are possible degree of minimal polynomial that are. Yeah, you can tell. Must degree of minimal polynomial. You write this. Little work I will give, that lunch take and finish. Mostly all theories completed. Maybe one have. After the question we will discuss. Less than 4 have. Less than 4 only have. No. Equal to 4 means correct. 4 also possibility. No? C don't tell. Otherwise less than equal to put. Then correct. Multiple choice time correct. Less than equal to. Yeah, null matrix is a nilpotent matrix. 1 degree. Zero. Oh, power 0 you are telling. -1 -2. No, not like that. That time, not like that. Degree is less than not possible first. Otherwise, don't take out this type thinking means. Otherwise, they will define R is greater than 0. or equal to 0, then you tick out. So, randomly I'm telling, if this type you will think means they will define a power r is greater than equal to 0, then C option is correct. Minus power and all, if you will think means, they will define everything, they will define. Always positive. Minus whenever choosing no in matrix, that will automatically will change in inverse. Lunch take and little this work you finish. You find annihilating polynomial and by that possible eigenvalue. Find h of lambda and possible eigenvalues. H of lambda means annihilating polynomial. First find for symmetric orthogonal matrix. Together, not separate this is. Second find for skew symmetric orthogonal matrix. Third, Hermitian unitary. Means two equation you will get. And by that both equation you have to solve and prepare new equation. After that, skew Hermitian unitary. Next, you can find only idempotent IT, involutory annihilating polynomial also can find. Enough. This 5 matrix, find annihilating polynomial and by annihilating polynomial possible eigenvalues. After that, after lunch we will see. Yes, symmetric orthogonal means two equation, A equal to A transpose, another one equation is A transpose is identity. Symmetric orthogonal means one matrix that is symmetric property also satisfying, orthogonal property also satisfying. So two equation you will get. A equal to A transpose, if you will put A transpose place, then A square equal to identity will happen. So annihilating polynomial is lambda square minus 1. So possible eigenvalue is 1 and minus 1. Okay, after lunch we will see. Think and do. Can't do means we'll discuss after lunch.